1,000 y's from that. If I do that, I'm going to end up with y triple prime of t plus 20 y double prime of t plus 200 y prime of t. And I can't set that equal to 0. It's not, is it? I don't know what it is, but you know what, so that I can keep track of it, let me call that alpha 1. I'm now saying I want this signal to be alpha 1. But how do I build alpha 1? Well, I take 0 and I subtract 10 or 1,000 of the outputs plus 1,000 of the inputs. And I said I had access to those. So what I can do is I can say take the input, x of t, scale it by 1,000, and put it into that summing junction as an input. Take the output, which is going to be down below. Let's say that's here. Let's say this is y of t. Scale it by 1,000, change the sign, and that now, when combined with the left-hand side, or alpha, all of those three inputs sum to produce alpha sub 1. But alpha sub 1 is just this. And what am I really trying to do? I'm really trying to find the output y. Why don't I integrate that? And that would reduce my derivatives by a power, or by 1. Meaning, if I now integrate alpha 1, I'm going to produce an alpha 2, and what's alpha 2 going to equal? That's the integral of alpha 1, isn't it? Which is y double prime plus 20 y prime plus 200 y. Oh, I have y. Let me subtract 200 y from that. So now I can say minus 200 y from alpha sub 2. Meaning now I take this and put it into a summing junction. Alpha sub 2 is one of my inputs. Now I take 200, change the sign, and subtract that from alpha sub 2, and what's left over? Alpha sub 3, which is y double prime plus 20 y prime. Questions on this? Do you see the process? And if I had an x up here, or its derivatives, I could just keep those flowing down. If I had an x, I would need to maybe add or subtract the opposite sign of it to eliminate it. And then I would put that in as another term in my summing junction. Meaning, this signal right here is now alpha sub 3. Alpha sub 3 is y double prime plus 20y prime. Why don't I integrate that one time? That's going to give me alpha sub 4. Alpha sub 4 is now this integral of alpha sub 3, which is y double prime of t plus 20y of t. What? I just was curious if you guys were staying awake. You like to make fun of me, so just keep doing it. I missed a prime, didn't I? Are we okay with this? Now what am I going to do? Get rid of that y piece. And I can do that by subtracting 20y. I can do that up here by taking that alpha sub 4, combining it with minus 20, scaling y. And now coming out of that summing junction could be alpha sub 5, which is just y prime. And I can get y from that by integrating alpha sub 5. I can go up here and I can now integrate this. There's y of t. That's the same as what I said was down here. And now I have my all integrator block diagram for this third order low pass Butterworth filter. I now have it in an all integrator block diagram. Questions on that? Does it seem consistent? How many integrators would you have expected? 3, since it's a third order system. Yes, sir. Why did I choose to do it this way versus the last way? Just to confuse you. Actually, just, thank you, you're welcome. No, just so you could see that it's not unique. And the way that you get things, maybe this technique works better for somebody than someone else. Maybe the other one technique works better for someone else. So do whatever you're comfortable with. I just wanted to show you another way of finding an all integrator block diagram. That's the only reason. Yes? So the input alpha is just 0. We could just erase that, couldn't we? We don't really need that. We don't need this signal. I'm going to leave it there, but for all intents and purposes, that's not there, is it? I'm just putting it there so that you understand that, oh, when I inject 1000x minus 1000y into a summing junction, what comes out? In this eventual block diagram, what's going to come out is that original expression reduced by those two terms. Yes. So now can we get the state space from this? How do we get our state space representation from this? So now we need to define our state variables. And what's the way that we define our state variables? If I gave you this block diagram on an exam, you better be able to give me a state space representation. That you should be barely awake and be able to do that. Okay? So that you should just be able to fall off your seat and do that one. So how do we do it? What's the only thing you have to remember to produce a state space representation from this block diagram or any block, all integrator block diagram? Pardon? The stuff coming out of those integrators, that's what I'm going to define my states. And just to be consistent with what I have done in my notes, let me call this output, and now I don't know what color to use. Let me call this Q sub 3. What? No. That's not consistent with my notes. Let me call it Q sub 1. So now Y is Q sub 1. Let me call this one Q sub 2. And this one, let me call Q sub 3. Now, I'm going to have to scroll down, but before I do, let's just see what's going to happen. What's Q1 prime? Q1 prime is alpha 5, isn't it? But Q1 prime is the output of this summing junction, so it needs to equal these inputs. It's going to be Q2 minus 20 Q1. And that will be in my first row. And how many inputs? Well, I'm sorry, how many x's? My actual system input enters into that first equation. None directly. It's going to eventually come in indirectly, doesn't it? At the very back. But it could have come in up here if there were terms if there were zeros in the numerator expression. Here we just had a constant, and so we just had this one input coming into the very first summing junction. But if we would have had some finite zeros, then we would have other coefficients upstairs, and they would be populating these additional, let's say, top from the top gains coming in from the input. Questions? Is the A matrix going to be 3 by 3? The A matrix is always square, isn't it? And you should expect it to have a dimension of 3 since you've now defined 3 states. So you answered your own question, right? So now you're just trying to get comfortable with what we're doing, and that's what I want. I want you to start getting very comfortable with all of these ideas. That's why we're sort of going back over them, sort of. What's Q sub 2 prime? It's right here at alpha 3, isn't it? But that's made up of Q sub 3 minus 200 Q1. And maybe you can start to visualize this A matrix. Q sub 3 prime is the one that's going to be maybe more interesting because now it's going to be directly forced by the input. And it only has one term in the A matrix. Meaning, if I go down and now create this state space, now that we have this all-integrator block diagram, we can now create a state space representation. And that's of this low-pass filter. There's the derivative vector. Then I have my A matrix, which is square times the state vector. Plus the input vector. Wow, I even scaled my screen and I'm still running out of room. Just give yourself enough room on the exam for a 10th order state space representation. But if I gave you a block diagram that was 10th order, it wouldn't be a problem, would it? It would take you maybe some time, but the process or the brain power, it wouldn't take much. Is that true? Are you feeling okay with that? If I gave you 10 integrators in a block diagram and I ask you what's the dimension of A, you're going to tell me, aren't you? 10 by 10. If that 10 integrator block diagram had 3 distinct inputs, what's the dimension of the input matrix B? It's 10 rows tall, 3 columns wide. It's 10 by 3. All right, so let's now fill this in from memory. What was Q1 prime? Didn't it have a Q sub 2? So that's going to be right there. It had no input. It had no Q sub 3. And it had a minus 20 Q sub 1. Questions on that? The next one, Q sub 2 prime, it had a Q sub 3. It had no Q sub 2. And it had a minus 200. And no input directly feeding it. And finally, the last row was minus 1,000, no other states, and 1,000 for the scaling on the input X. Which, if now somebody gave you the transfer function, you could immediately fill in this matrix. This upper diagonal is going to be 1s. Nothing other than this first entry in the last row But I think for now, you guys probably should just sort of go through that process so you feel comfortable with where these coefficients are coming from. But you could, from a transfer function, immediately plop this down. The other thing that you need is the output equation. And we only had one output in this example. And what is this state space? This state space is a third-order Butterworth with a bandwidth of 10 radians per second. Now I have an output matrix times the state vector plus the direct feed-through term times the input x. But my block diagram, I assigned the output to just be the first state, and there was no input directly feeding in to help create the output y, and this is now my output equation. Questions on that? And you could have just left off this last piece, this 0x, unless I ask you for d, then you'll want to give me what d is. D is now a scalar that's it's a matrix that's 1 by 1, which is a scalar, and it's 0. It doesn't have to always be 0, but in this case, because we had the transfer function that we had, it was strictly proper, meaning the numerator polynomial was less degree than the denominator. We don't have any direct feed-through path from the input to the output. And so we would have expected D, the D matrix, to be 0. That is now our continuous time state space representation. And that wasn't that hard to produce, was it? Somebody asked, can we get a state space? That was the question I was hoping was floating around in your head, right? Now what can we do? Maybe now you say, I don't want to simulate this. I kind of want to just crunch the numbers. Maybe I want to put this into a spreadsheet, an Excel spreadsheet, and filter some waveform. I want a recursive formula. I want to now take this to discrete time. Now we can. Now that we have this, this is now our A matrix. Here is our B matrix. Here is our C matrix. And there's our D matrix. Now what I want to do is jump into chapter 5. And as I said, this is really more for your enjoyment. Let's now look at a discrete time approximation of this third order low pass Butterworth state space representation. Let's create a discrete time state space representation. And we don't have to do anything more than what we've already learned when we did it for, I think, a first order or a scalar system. What you have to remember, though, is when I now write down Q prime, that's a vector of Q's. Buried inside Q is the first component, Q sub 1, primed, the second component primed, and the third component. We started with a third order. So Q prime is now Q1 prime, Q2 prime, and Q sub 3 prime. The question was, are there other ways of denoting that this is a matrix or a vector? There's all sorts of ways. You pull off any book from a bookshelf and they may have their own way. They're usually bold or maybe, I don't know, an underbar, but I can't distinguish, so it's clear from the context. How's that? Can I be any more difficult? So from context, it should be clear that Q, it's obvious, right? It's obvious that that's a vector. And it could be a 1 by 1 vector, couldn't it? If you had a first order system, that could be just a scalar. But now what we want to do is we want to approximate this derivative, which is just delta Q over delta T. We're simply going to approximate that in the following way. We're going to take Q, one time sample in front of another Q, and divide it by the time separation in those arguments. And L I'm just using as an index on my time. If I had a time axis, it could be in seconds, but I might just index it with respect to L. But L times capital T gives me the actual time in continuous time, in the continuous time setting. Little l equal to 1 times cap t. If cap t is 0.01, 10 milliseconds, then that just says, oh, q of 1t is q at time 10 milliseconds. The next one beyond that is 20 milliseconds. So this is now q at 20 minus q of 10 over their time separation, which is 10 milliseconds, or 0.01. That's how I'm approximating this derivative. That's why this is an approximation of the original set of equations. This now allows me to replace on the left-hand side of that set of equations q of lt plus t minus q of lt, and remember, it's clear from the context that those are vectors, divided by t, and that's now approximately equal to a times q of t plus b times the input. Whoops. I'm sleeping. I needed to make this lt and this lt. And it should be clear from my voice that that t was a capital T and not little t. Oh, this is getting pretty bad, isn't it? Now you actually have to be awake, paying attention, because that t may not be clear unless you look up at the board occasionally. What t is he talking about? Sometimes it's capital T, which is a sample period. Sometimes it's little t, which is the continuous time variable. Let me now clear that capital T. Capital T is a scalar. That's not a matrix, is it? Capital T is just a number, and we were just using for grins capital T equal to 0.01. That's a lot of times what we pick for a sample period anyway. This is now 0.01. I'm going to multiply both sides through by that number, capital T, and I'm going to leave it as a capital T. So that now I have q of lt plus t minus q of lt is approximately equal to at q of lt. And now, what am I doing? This is maybe a little bit too much detail, but capital T is a scalar. If it was a matrix, I couldn't just slide it on either side of that A. But I'm used to saying AT, so I put it on the right. But capital T is a scalar. It could have been TA. Doesn't matter. If it was matrices, you can't be, matrices don't naturally commute. You can't say AB is equal to BA. So, but capital T is a scalar, that's okay. And I'm going to then put here a BT x of LT. And what I want to do now is put everything over on the right-hand side except for this next state, which is this guy. And remember, by context, this is a vector, isn't it? So this is q sub 1, which was the output, q sub 2, and q sub 3. Approximations to that at a particular discrete instant of time. I want to now combine this piece with that A on the other side, so I'm going to inject artificially an identity matrix. How big is that identity matrix in our example that we've been playing with? How big was A? It was 3 by 3, so this I has to be a 3 by 3, and the identity matrix is just ones on the diagonal of a 3 by 3. Everything else is 0. Now I can push that second term on the left onto the right-hand side, and I'm left with the equation that I want. I want Q of LT plus T to be approximately AT plus I times Q of LT plus BT x of LT. And what I can now do is, this is just a matrix, isn't it? I'm going to call that A sub D. That's now my discrete time system matrix. This is just my original input matrix scaled by a scalar, capital T. I'm just going to call it a new matrix, B sub D. This is now a discrete time system equation in the state space formulation. This is a third order vector equaling 3 by 3 matrix times a 3 by 1 vector plus a 3 by 1 column vector times the input. That's now a difference equation in state space form. What's my output equation? I can sample my output exactly at the same instance that I'm collecting all of these states and the inputs at those instances. Y was just C x of t, or C q of t. There were no dynamics, so the C q of LT, and to be general, I could say D x of LT. And that C is exactly the same as the C sub D if I wanted to subscript my discrete time. This structure on the output is exactly the same as the continuous time output matrix structure. We're almost there, but what have I not done yet? Although I kind of have, by talking about capital T being 10 milliseconds or 0.01, I really haven't defined capital T, have I? So let me show you a way that you could find that. How would you pick capital T, knowing what you know about this system? What is capital T? Which is the sample period. And how are we going to find that? I can't just always assume that it's 0.01. What if I had a low-pass filter that was 10,000 hertz in bandwidth? You know the eigenvalues of A are the poles of your system. But the more important thing to maybe keep track of is, what's the magnitude of those poles? Or what are the magnitudes of those eigenvalues? Remember, I did the absolute on my poles. How far away from the origin were those poles on that semicircular arc for this particular example? They were 10, weren't they? They were 10 radians per second. So I know the bandwidth of my low-pass filter. That's what's key. I know the bandwidth. And maybe that's what people would first think of. Maybe they wouldn't first think of the eigenvalues of A. But you know, if I wanted to try to confuse you, I could say, just go with the eigenvalues of A. What? Where'd that come from? Well, if you're following along, you know that's just the poles of your system. That's just H of S. But now the bandwidth of this low-pass filter is the radial distance away from the origin of those poles or those eigenvalues. And that's 10. Meaning, if we now needed to sketch this as a Bode plot, we would be flat until where? And then we're going to go down how far, or at what rate? For this example, it's minus 60 dB per decade, and this particular point where our two straight lines meet is our cutoff frequency, or our bandwidth. That's the omega naught, equal to 10 radians per second, and that's our cutoff frequency. So what? We wanted capital T. You haven't told me what T is. You've told me the bandwidth. Who cares? Well, that's important because you want to preserve this behavior. And what are you trying to preserve? Well, you want to preserve signals, sinusoids, that are going as rapidly as 10 radians per second. And we just found out that's not very rapid, is it? That's less than 2 hertz. But 10 sounds bigger than 2, but that's in radians per second. We now have sinusoids that are DC up to 10 radians per second that we would like to treat nicely. We want to pass those. We're low-pass filtering. This now tells us that if we're trying to capture that information, if we were simulating it, how fast would we sample something that was at 10 radians per second? What have we sort of agreed to as far as our rule of thumb? We might want to sample at 30 to 60 times the filter's bandwidth. And this is just a rule of thumb. All right, so let's now see if we call omega sub s our sampling frequency in radians per second. We now are saying that that's 60 times omega naught. So now I'm calling this the omega naught. That omega naught is 10. And I want to sample, so whenever I pick capital T, it's going to be related to omega sub s. Remember what I told you not to forget before you retire? Omega is 2 pi f, but f is 1 over t. So you know omega is 2 pi over t. So if I can find omega sub s, I can find t, how fast I want to sample. This now says that I am going to be at 60 times 10, or I would like to sample at 600 radians per second or faster. So that's how many, or that's the frequency of my sampling. And now I want to translate that into how fine do I chop up my axis. And this is what I just commented on. You know that omega sub s is 2 pi f sub s. That's your sampling frequency in hertz. Somebody might say, oh, I'm sampling at 10 kilohertz. Well, that's what this f sub s represents. They usually don't tell you the sampling frequency in omega sub s. How fast do you sample in a digital audio system? Come on, you're supposed to answer that because I don't know. Isn't it 44,000? We can hear about 20,000. So they, because of Nyquist, they go beyond 40,000 and they've gone up to 44,000 hertz to sample. That's for digital audio. For us, we're saying 60 times the bandwidth or 30 times. We went 60 this time, but I said that f sub s is actually probably, I would like to call that t sub s, but in the discussion I was just calling it t, so let me just call it t for now. Is that clear? And what did I find just up above? That was equal to 600. Oh boy, these numbers are just too neat, aren't they? So this now, if I solve this for t, that's now 2 pi over 600. But I can throw away the irrational part of pi. We're trying to be a little more rational today. No, I can err on the side of making t smaller. Pi is 3.14159 something. Well, I can throw that 1.5 away, 14159 away, and not penalize myself in terms of sampling. This is now 6 over 600. Well, what do you know? The 0.01 seconds. No, you can't always sample at 0.01 seconds. What drives that 0.01 seconds? This guy, didn't it? 600. And where did that 600 come from? Your bandwidth. Now if you sampled at 10,000 hertz, what would that 10 become? 2 pi times 10,000, right? That's now 20,000 pi. Oh, I wish I had that many pies, but they'd spoil before I could eat them all, right? So now I have 20,000 pi times 60. 120,000 pi. You want to convert that to dollars, right? 120,000 pi. But you get the idea. You wouldn't be sampling at 0.01 unless you wanted to have aliasing and everything else going on, and we'll talk about that in subsequent lectures. Let's look at a little of this in terms of MATLAB, or see if we can. Is everyone clear on what we've done? We started with a low-pass filter, we discretized it, we put it into state space, and now we found out how fast to sample it, what capital T to pick, and now we can start playing in MATLAB if we want. We can start simulating this. So let's just go through this process. Let's say now to simulate the low-pass filter discussion. We had an A matrix in the continuous time, and that was then this minus 21 comma 0 semicolon 0 or minus 200 0 1 semicolon minus 1,000 0 0. That's our A matrix. In continuous time. And it seems like people like to talk about the eigenvalues. So let's just do the eigenvalues. That'll make us feel good, right? We now find the eigenvalues. Those are the same as the poles of our system. We can find the input matrix B. That was 0 semicolon 0 semicolon 1,000. There's our input matrix for the continuous time system. We had our output matrix C, which was 1 comma 0 0. And our D matrix, if we wanted to put it in there formally, what did I call that? Input feed-through matrix. What? Feed-through matrix. I think I did just call it the feed-through matrix, didn't I? Now, what was T? Capital T, we just found to be 0.01. And that's what we're calling our sample period. We can now create our discrete time system. We can say A discrete, or AD, is now equal to A times capital T plus the identity matrix. Well, MATLAB is kind of cute. It says if you just say EYE 3, that will give you an identity that's 3 by 3. I3. That's now your discrete time, and you could now say, what are the eigenvalues of my discrete time system? And you go, would you quit talking about eigenvalues? Enough. But now what do we have? Does that make sense? Well, we started with complex, didn't we? 2 complex conjugate poles and 1 real. We have 1 real and we have 2 complex conjugates. Let's look at the absolute value. If I could type. I don't want to do the Lincoln of that. That was Abe. So this is ABS. You may not be a, and that's not anti-lock braking system. That's the absolute value or magnitude. So now those are what? If you compare those to 1, now they're all inside the unit circle, all inside the unit disk. If you get into discrete time processing, the stability region now is this finite region in the z-plane, and it's just the unit circle. We've gone from the entire complex S-plane, left half being stable, we've now collapsed that down to just the unit's disk in the z-plane. But these all have magnitude less than 1, so our system is stable. That's good. We didn't create an unstable discrete time system by sampling a continuous time stable system. Where was I before I got off on this eigenvalue kick? I was talking about Abe Lincoln, wasn't I? Oh, I need the discrete time input matrix, which is BD, which is B times capital T. And I need the discrete time output matrix. That shouldn't surprise you. That's the same as the continuous time output matrix. Now let me run some simulations. Let me just create, well, what's the transient response going to be for this system, and how would I maybe think about that? How long should I run this simulation if I was just interested in following the transient? I'm looking at the eigenvalue question. What did the poles tell us? What do the poles tell us? Where are they? We're looking at the real part of those poles, aren't we? And we're looking at the slowest one. That was minus 1/2 before we denormalized it, and then it moved by a factor of 10. It's now minus 5, isn't it? That's going to give us an e to the minus 5t piece for a decay, and that's going to be the slowest decay. So 5t, 5 tau equal to 1. Tau is now 0.2. And we want 5 of those time constants, and that's how long our transient's going to be. So our transient is going to last about a second. And now what I want to do, what am I passing in terms of frequencies? 10, right? So that was a little bit less than 2 hertz. Well, I may want to see a few periods of oscillation. Cutting a long story short, let me say time. Yeah, I'm making it even longer, aren't I? So time is now 0 up to, I have to use the same sample period, capital T, and now let me just go 5 seconds. That's now my time axis, and let me build an input that is the combination or the sum of something that I want to see or to pass, which is a 5 radian per second. That's in the band pass region of my low pass filter. And now let me put something that's not quite as big in magnitude, but it's at a higher frequency. Let's put it a decade beyond the cutoff frequency. It's now at 20 T. So this now is representing a noisy input signal. Now my system 1 in discrete time is going to be state space AD, BD, CD, CD 0, and now if MATLAB's pretty smart, you can use the same command or function SS for continuous time or discrete. If you want it to be discrete, you have to tell it what your sampling period is as an extra argument, and that's capital T. So there is my system. And there it is. Now what I want to do is I want to simulate this. And again, MATLAB's smart. It knows what system 1 is. It knows it's a discrete time system. And I'm putting in an input X. And this I'm going to say for Y is now my filtered output waveform. If I could type. What was my system called? Oh, good. So everybody see that? It was 1D, wasn't it? Whoops, what did I just do? I don't know where my cursor is. All right, so I hid it from you, but now I want to plot it. So now let me plot time versus the output, and let me make that dashed, and then let me plot the unfiltered version, X, as a solid line. And that's now my result. My green is my noisy input. The dashed blue is my output. And how long did it take before I got to sort of a steady state? About 1 second, and that's what we expected. And then I get into this steady state, and what do I see? Pretty much a 5 radian per second output. I filtered out this noise, where that noise was coming in at 20 radians per second. We'll have to stop there. I could go on, but you have other things that I'm sure you want to do. But thank you for your patience, and we'll see you next week.